Okay, going to be working the first homework assignment in the book, which is called Basic Definitions and Terminology. And we're starting with number 1. And I'm going to take my time through this. I'm going to write all this down to the best of my ability. That way we can discuss the results in detail, I suppose. Alright, so we're asked to determine whether or not this is a linear or nonlinear differential equation, and we're also asked to give the order of each of the equations. So let's start with the order because I believe that will be easier. Let's start. I messed up there. I put to the end. That's a double prime there. So the order here is going to be the highest derivative that we see being taken here, which is going to, in this case, be the second order, or second derivative. So this is going to be a second order differential equation. And now we want to determine if it's linear or nonlinear. So what we need to be looking at is in front of each of these y terms, whether or not they be y, y prime, y double prime, that this out in front is some function of x. So the textbook, I might take a little more time here on this first one. The textbook describes that the order here, that this should be, in this case, a sub 2 of x. Since we have the second derivative here, this is like the second coefficient function in front of our second derivative of y. So this needs to be a function of x, in which case it is. 1 minus x is a function of x. Now we can move to the second term. Notice what's in front here is also a function of x. This would be a sub 1 of x. And then we can have a y term as long as what's in front of the y term is also some function of x, a sub 0 of x. And 5 by itself is a constant function, so therefore this does qualify as being a function of x. Now the other side of the equation here equals cosine x is also some function of x, g of x. So if you look on page 3, this kind of matches exactly what we have there written in blue on the bottom of the page. So everything looks good here in terms of the requirements for it being linear. So this will be a linear second order differential equation. All right, now let's move on to number 2. So for number 2, we have x, and we have d3y over d. You know what? I might make my lines a little bit bigger here. Eee, that didn't help. That's okay. I'll start it this way. 2. So we have x, and then we have d3y. This is the third derivative of y with respect to x, and then minus 2, and then we have derivative of y with respect to x, just the first derivative, all of that to the fourth power, and then plus y equals 0. So again, let's start with the order. So what is the highest derivative we see here? And in this case, it's the third derivative. So the order here would be third order. Now the question is whether or not it's linear or nonlinear. So we look again in front here. Is this a function of x? Yes, it is. This is a function of x also. And then we have y by itself. You can look at the y in front. That's a function of x. And then over here you could say that that's a function of x. But we have an issue. The issue is that our derivative is being raised to the fourth power. And because of that, if any of your derivatives, whether it be the third derivative or the first derivative, doesn't matter which one, if either one of those is raised to a power other than 1, this is going to be nonlinear. So because of that in blue, this is going to be nonlinear. Okay. Now, next one, 3. Is going to be y prime plus 2y equals 1 plus x squared. All right, so let's take a look here. How about the order? Well, the highest derivative I see is the y prime there, so this is definitely going to be a first order. Okay, and now is it linear or nonlinear? And we notice right away that we have a problem. So I'm going to highlight the problem in blue. This factor out in front of that y prime is not a function of x. And that's what we need in order to call this a linear differential equation. So right away we have violated the property. So this will be nonlinear. Okay, now just to speak about it, this would be okay. That plus 2 would be okay. That's a function of x. And the other side of the equation is a function of x. So everything else looks good. It's just that one y sitting out there in front. All right, let's go ahead and move on to number 4. So for 4, we have x squared dy plus, and then in parentheses, y minus xy minus x e to the x dx equals 0. So what you can imagine doing here is if we could take every term and divide by dx. So I'll just divide this by dx and divide this by dx. Then what we would have now is x squared dy dx plus, now this would go away, it's like a 1, and so you'd have y minus xy minus x e to the x, and then equals 0 divided by dx is still 0. And so now let's check some things. How about the order? Well, here we go. We've got this right here, our first derivative. That means we've got a first order differential equation, because the highest derivative we take is the first derivative. So we have first order. Now let's check to see if it's linear. So in front of this y term, that is a function of x. In front of this y term, we have 1. That is a function of x. In front of this y term, we have this negative x here. That is a function of x. And then this right here by itself with no y's at all is also a function of x. So you can imagine if you move this to the other side, it would be x e to the x. And that would be like the g of x I'm trying to match it to that equation, I think, on page 3. So this all looks good. This is going to be linear. And we are set. Now you might be asking, like, is it okay that we have 2 terms with y in it? Well, it's fine, because what we could do with that is we could actually factor the y out, and we could have written that as 1 minus x times y, and then of course that 1 minus x is a function of x. So it doesn't matter that there were 2 terms there with y in it. All right, moving along. Number 5. Okay, we have x cubed, y, and then up here in parentheses 4, and then minus x squared, y double prime plus 4x y prime minus 3y equals 0. All right, so let's talk about the order. I see let's see, what does this mean? That means take the 4th derivative. This means take the 2nd derivative. This is the 1st derivative. So it looks like I'm in order 4 here, 4th order. And now let's check for the linearity. So we have a constant here, or not a constant, I should say, a function of x in front of that 4th derivative. Here we have a function of x. Here we have a function of x. And then here, this is the y without a derivative, so we have a function of x in front of that. So all seems good. And on the other side, this right here is also some function of x, the constant 0 function, but it is still a function of x. So we are also linear here. Okay, 6th problem here. I imagine that these videos are going to take me quite some time to get through. In fact, I might be making multiple videos. Okay, here we go. All right, so let's check the order here. The highest derivative that I see here is this right here. It's a 2nd derivative. So we've got a 2nd order. And Now we start looking the coefficient in front here. That's just 1, and that is a function of x, so I'm good. Here with this y term in front of that, I've got a function of x. It's a constant, but it's a function of x. And then I've got a problem. Okay, the problem I have here is that this y is inside of this sign. It's the argument of the sine function. So you can't look at the sign out in front as being like some function of x. It's not. It's the y is its sine of y. So does this qualify? Well, it doesn't, because what we need is in front of the y to be multiplication times some function of x, not composition. So this doesn't qualify. We would need something like a y out here like that multiplied, but then even then it would fail because this would not be a function of x. So this just fails all the way around, so this is just nonlinear. Now, had that been sine x, we would be okay. But it's not sine x. All right, so let's see, 7 dy dx equals square root of 1 plus, and then the second derivative of y with respect to x, all of that squared. All right, let's talk about the order first. We have a second derivative appearing in here, so this is going to be second order. Notice that we did have a first derivative right here, right? But the highest one that we see is the second derivative. Okay, now let's talk about linearity. So in front of this right here, this is a 1. That is, could be considered a function of x. But on the other side, we got all sorts of trouble. We've got a root, but more importantly, we've got this squared. So we're squaring the derivative, and once we square the derivative, any of the derivatives, or even if we square y itself, okay, we are in trouble. So this is going to be, well, I'm not going to say trouble. We're just nonlinear. That's not necessarily trouble. It's just nonlinear. Okay, let's move on. Oh, scroll back up a little bit. Let's look at number 8. So for number 8, we have the second derivative of r with respect to t, and then equals negative some constant over r squared. Okay, so the independent variable in this problem is r, is the independent variable. And the dependent variable, I'm sorry, I got that wrong, t is the independent variable, and then r is the dependent variable. So we are assuming here that r depends on t, kind of like y depends on x. So let's talk about the order. First of all, we have a second derivative of r with respect to t, so our order is the second order differential equation. Now, in terms of linearity, in front of this we have a 1, so what we would need there is a function of t, now, right? We would need a sub 2 of t instead of a sub 2 of x, because t is our independent variable. So this 1 is a function of t. It's a constant function, but you could consider that a function of t. And then the other side, we got all sorts of trouble. So let's look at this as being negative k times 1 over r squared. That's one way we could look at it. So this out here in front is like a constant, which you could look at that as some function, cause, you know, a sub something, I don't know, of t. You could look at that constant as some function of t. But the problem is this right here, 1 over r squared, does not look like if you look back at the formula on page 3, it says that, you know, we can have the you know, second derivative of y, first derivative of y, third derivative of y. We can have y by itself, and then we could have had a function of x. Well, it doesn't say anything about having this. This would be like us having a y to the negative 2 in that formula, and there's nothing about negative exponents in there. It just says that we can have y and we can have some function of x in front of it. It doesn't talk anything about having negative exponent powers. So right here at this point, we can say this is nonlinear. I guess you could say that y to the first power makes that term linear, and the r to the negative 2 here, or 1 over r squared, makes it nonlinear. Okay, moving along. Number 9. Sine of x, y triple prime, minus cosine x times y prime equals 2. All right, the order here, third derivative of y. So the order is third order. And then in terms of linearity, out here in front of that third derivative, that's a function of x. Out here in front of the first derivative, that is a function of x. And then over here, by itself, on the other side, is some function of x, like we call that g of x. So everything looks really good here. So this is going to be third order and linear. All right, number 10. Okay, for number 10, we have 1 minus y squared sitting in front of dx, and then plus x, and then dy, and then equals 0. So now let's go ahead and let's divide through by dx again. And that will give me, let me do it over here because I'm running out of room. I'll have 1 minus y squared, and then this here becomes a 1, so it's not really necessary for me to write that. And then I have x dy dx equals 0. Oh, I forgot to write it, even though I knew it was going to be 0 dx over here. Okay, so in terms of the order, we've got only the first derivative appearing here, so this is first order. And then in terms of linearity, in front of this first derivative is a function of x. And then what's left here is not a function of x, it is a function of y. It would be fine if that was just 1, but it's that y squared that causes a problem. So this is definitely going to not be linear, so nonlinear. You know, had this right here, had that 2 not been there, you know, had that just be to the first power, we'd be okay, but it was because it's squared that causes the issue. Okay, that's the first 10. I'm going to stop this video and pick up the next set of problems on a different video. Oops. Okay, going to be picking up here on number 11 now. Okay, so for these problems, what we're asked to do is, well, we're given a differential equation. And then what we're asked to do is take a look at the following equation, y equals, let's say in this case, e to the negative 1/2 x. And we're asked to verify that that equation is, or that function is a solution to this equation. So what I need to do here is work over here on the right first. I need to take a derivative. So we're only going to need the first derivative here in the equation. So I'm just going to take the first derivative here and just applying a little chain rule here. Well, I'll do it a little slower. The derivative of e to anything is itself, and then times the derivative of what's up here, and derivative of that is just negative 1/2. So what we get is negative 1/2 e to the negative 1/2 x. Okay, so now what I do is I start rewriting this equation on the left side. So I'm going to have, well, what happened up here? Why does it look so weird? Let me try this and bring it back. Okay, so let me rewrite this equation, and I'll do it in green. So we have 2, and then y prime, which y prime was this right here, so I'm just going to put that here, so times negative 1/2, let's see, e to the negative 1/2 x, and then plus y, and remember y was this, so that's just, yeah, e to the negative 1/2 x. And what we want to figure out is whether or not that is equal to 0. So that is a question. Is this equal to 0 or not? So we just work it out and notice that the 2's here cancel. So we just get negative e to the negative 1/2 x plus e to the negative 1/2 x. And those are the exact same things, except they're opposite in sign. So when you add them up, you get 0. So it checks. That is a solution to that differential equation. All right, let's take a look at number 12. Number 12, y prime plus 4y equals 32. And the equation we're looking at, the function is y is 8. I only need the first derivative here, right? First derivative is a first order differential equation, so I'm going to go ahead and take the derivative of this, and lo and behold, derivative of a constant is 0. So I'm just going to now go back and start plugging in. So this becomes 0 plus 4 times y, but y is 8, so 4 times 8. And I want to make sure, does that equal 32? And it does. It's just some arithmetic here, so checks out. Pretty straightforward on that one. Let's take a look at 13. This is definitely going to get more interesting. Okay, we have dy dx. All right, minus 2y equals e to the 3x. And the function I'm looking at is y equals e to the 3x plus 10 times e to the 2x. All right, I'm only going to need the first derivative here, so let's just take the first derivative over here. I'll use the Leibniz notation, dy dx instead of y prime equals the derivative of this, so same thing as before, derivative e to anything is itself, but then times the derivative of what's up here. So I'm going to have a 3 pop out the front. And then over here, the 10's just going to come for the ride. I need derivative of this, same sort of thing. We're going to have a little chain rule there. The 2's going to pop out. So I'm going to get a 20 e to the 2x there when I take the derivative. So now what we do is we rewrite everything. So we start off by writing dy dx, which we just found right here. So this is 3e to the 3x plus 20 e to the 2x minus 2 times, now we need y. And remember, y is all this. So e to the 3x plus 10 e to the 2x. And we need, hopefully, for this to be equal at the end to e to the 3x. Also pay attention, the parentheses around here were necessary because we're multiplying negative 2 times y. So we've got 3e to the 3x plus 20e to the 2x minus 2e to the 3x minus 20e to the 2x. So that's just distribution of that negative 2 through. And the question is, what does this turn out to be? So we've got these cancel, and then I got 3 of these, and I'm taking away 2 of those, and that means when I'm done, I'm just going to have 1 of them, e to the 3x. And that does check off right there. So it is a solution. All of these should work out. They're asking you here to verify. It's just getting us used to the mechanics of testing these things. So dy dx plus 20y equals 24. And the function that we're going to take a look at right now is y equals 6/5 minus 6/5 e to the negative 20t. So our independent variable here is, wait a minute, hold on. This was dy dt over here. I was going to say our independent variable is t, not x. All right, so I'm going to need just the first derivative here. So I'm going to take the first derivative. Derivative of a constant here is 0, right? So I don't need to write that. Okay, so that's 0. Then over here, the negative 6/5 comes for the ride. Then when we do this, we've done this a few times now, that negative 20 up top is going to pop out, e to the negative 20t. And then we get some simplification on this right here. 5 goes into 20 4 times, and then negative 6 times negative 4, that's going to be 24 e to the negative 20t. All right, so that's our derivative. We're ready to start plugging in. So this becomes 24 e to the negative 20t plus 20 times, here comes that very important parentheses again, times y, and here is y. So I've got 6/5 minus 6/5 e to the negative 20t, and we're hoping at the end of this that it's going to be equal to 24. So let's see what happens. Distribute here and here. So 24 e to the negative 20t plus 20 times 6/5 is going to give us 24. And then when we do 20 times negative 6/5, I get negative 24, and then e to the negative 20t. And at this point, this term and this term cancel, and we're just left with 24, which checks out. All right. Quick pause here, check something. All right, I can continue now. 15. Really just kind of not happy with my microphone. I've got great microphones. I think it's my laptop. The jack, the port for my setup here is, I think I've got problems with it, but not going to get a new laptop because of that. Okay, so here we go. All right, so here's our differential equation, and the function that we want to test here is 5 tangent of 5x. All right, so we are only going to need the first derivative again, so let's go ahead and take the first derivative. All right, the 5 is going to come for the ride. Now, derivative of tangent is secant squared, so secant squared of the argument, which is 5x. And chain rule says take derivative of what's in here, and that's 5. So at the end of all this, we're just going to get 25 secant squared of 5x. That is our first derivative. Now let's start plugging in, see what happens. So here we have 25 secant squared of 5x. And then the question is, does that equal, so I'm going to do this one a little different. I'm asking this question, is this equal to 25 plus y squared? So here's y. If I square it, what happens? So if I square the 5, I get 25. If I square tangent, I get tangent squared of 5x. So that's what would happen if I were to actually square this entire thing. So it doesn't look like they match right away, but if we just do some Precal identities here, let's factor out of 25. If we do that, we get 1 plus tangent squared x, tangent squared of 5x. And that is a Pythagorean identity. We have an identity, I'll write it here on the side, 1 plus tan x, or I'll say tan squared theta equals secant squared theta. So that is an identity. So this actually becomes 25 secant squared of 5x. And that does check out to match this side. So yes, indeed, that is a solution. Okay, let's move to the next page. I'm on 16. So dy dx equals square root of y over x. Square root of y over x. And then y is given to us to be equal to, square root of x plus c sub 1, some constant, squared, where x is greater than 0 and c1 is greater than 0. All right, so those are the things that are given to us. Let's go ahead and recognize that my computers are acting really weird. That we only need the first derivative, so let's go ahead and take that. So the derivative of this, first we need to take care of this chain rule here. So we've got the second power here, that's going to have to pop out front. We're going to have root x plus c sub 1 to the first power. Now I don't need the first power, but I'm just pointing out that's what happens when we take derivative. And then we need to multiply times the derivative of what's inside here. And the derivative of what's inside with respect to x, the derivative of the square root of x is 1 over 2 root x, and the derivative of a constant is 0. So that's the derivative of what's in here. Now let's just try and clean this up a little bit. This is 2 parentheses root x plus c sub 1 times 1 over 2 root x, and the 0 is gone, so I don't need the parentheses anymore. The 2's cancel, and I guess maybe I can distribute this through. So 1 over root x times the root x, that's going to give me 1, and then I should get c1 over root x. That should be it. And that's my y prime. So let's check this now. Coming over here, we've got dy dx, which is 1 plus c sub 1 over root x. And the question is, does that equal the square root, ooh, that's shaky, of y, now remember this is y here, that's square root of x plus c1 squared over x, and x is just x. So let's see what happens here. If we were to just rewrite the first side here, does that equal, okay, so I'm going to split this into two roots here. So I can do like the square root of the top and then over the square root of the bottom. And that would be, when I take the square root of that squared, I should just get root x plus c1 over, and then on the bottom I'm going to have the root of x, so root x. And this is looking pretty good because I can split the right side up. Since they have the same denominator, I just do like the root x over root x and then plus c1 over root x. So I should just get 1 plus c1 over root x, which checks out. That does match this side. All right, 17. Okay, y prime plus y equals sine x. And then we've got y is equal to 1/2 sine x minus 1/2 cosine x plus 10 e to the negative x. Be careful with that negative. All right, so I'm going to need just the first derivative here. And so my derivative is, okay, half comes for the ride, derivative of sine of x is cosine x. Next one, negative 1/2 comes for the ride, but derivative of cosine is negative sine, so it's going to change it to a plus 1/2 sine x. And then over here we're going to have this e to the negative x. The derivative of that is itself. The 10 comes for the ride, but then we're going to get a negative 1 to pop whenever we take chain rules, so we should get a negative 10 e to the negative x there when we take its derivative. And then let's check it. So here y prime is 1/2 cosine x plus 1/2 sine x, and then minus 10 e to the negative x. That's y. And then plus, now we're going to do y prime here. I'm sorry, that's y prime. Now I'm going to do y. Y is this right here. So I've got 1/2 sine x minus 1/2 cosine x plus 10 e to the negative x. And what I want to know is whether or not, does that equal, question mark, does that equal sine x? So let's see, I'm sure things are going to cancel here. I've got the half cosine x, negative half cosine x gone. The negative 10 e to the negative x is gone with the 10 e to the negative x. And I just have these two terms are the same, where I add them up together, and that means half plus half is a whole, so you've got an entire sine x here, 1 sine x, and that does equal the other side. Check. All right. Looking good, looking good. Look at that one there. 18. Okay, 2xy dx plus x squared plus 2y dy equals 0. Okay, that's our equation. And then we're trying to check this with y is equal to negative x to the negative 2. So I wrote it a little different. They have negative 1 over x squared in the book, but I'm going to take a derivative, so I'm going to use power rule, so I just brought that up. All right, before I begin, what derivative do I need? Well, I would divide everything through by dx. Divide by dx. Divide by dx. And when that happens, this is going to go away. It's going to be dy over dx, and then this one's going to be 0. So let's just imagine that I do all that. I don't want to have to rewrite that whole thing. So backing this up. So this is going to be gone here. This right here is going to become dy dx, and everything else is going to stay the same. Okay, so let's check. Oh, I need the derivative. Oops. I was trying to point out that I need the first derivative. So dy dx, using Leibniz notation, is actually going to be positive 2 x to the negative 3. So that's our little power rule. This is the same as 2 over x cubed. All right, here we go. Let's start writing some things down here. We're checking now. What is 2 times x times y? Well, that's 2 times x, but y, remember, is this. Or if you'd like, it's this. So I'll do it this way. Negative 1 over x squared. Plus, now x squared plus 2 times y. Y was negative 1 over x squared. Then all of that times dy dx, which was 2 over x cubed. And the question is whether or not that's 0. So let's see. All right, so first of all, when we put these two together here, do that, it's going to become negative 2 over x. Okay, so the x on top here cancels with one of the factors down there. You still have one factor of x on the bottom. All right, let me just kind of clean this up a little bit. Well, yeah, I can distribute now. Just keep in mind that this piece right here, I'm going to erase it. That's really just going to become minus 2 over that, okay? So now we distribute this through here and distribute that to here. Let's see what happens. So when we go here to here, we get a positive 2 on top, and then we only have one more x left on the bottom. And then the next thing we have is, let's see, here to here, this piece. That should give me negative 4 on top, and then x to the 5th on the bottom. Yeah, let me see, make sure everything looks good here. Dy dx 0. Oh, you know what? Oh, okay. Well, this is a good problem because you know what? This is not working. This is going to cancel. This does not equal 0. I thought there was a problem, and I see my problem. I actually wrote down, I was looking up at the book, I wrote the function from the problem below it. So this is a good example of, hey, look, this is the function that is not a solution to this differential equation. Yeah, that was just a fun exercise. All right, let's go back. Just pay a little more attention to what I'm writing down over here. All right, let's try this again. So number 18, the function is actually x squared y plus y squared equals c1. Okay. Now, at this point, I need dy dx. And this is the first time this has happened. Our equation on the side here, we're going to have to take derivative implicitly. So we're going to take the derivative on the left side with respect to x, and then the derivative on the right side with respect to x. So keep in mind when we do this, the derivative right here, we have a product rule between those two. When we take our derivative, we're going to get the derivative of x squared, which is 2x, times y, plus, this is product rule here, now the derivative of the y, which is your dy dx, times the x squared. So there's that product rule on that first little piece here. Then we have a plus sign, so I can say plus, and now we need derivative of y squared. Derivative of y squared is 2y, but then times the derivative of what's down here in the base, which is dy dx. And that must equal the derivative of the right side with respect to x, which is 0. Okay, now what is this? I need to try and solve for dy dx over here. So I need to get dy dx by itself. So both of these terms, this one and this one, have dy dx in it. So what I'm going to do is leave those over there on the left-hand side. And then I'm going to move the 2xy to the other side, so it becomes negative 2xy. Then I'm going to factor out dy dx on the left side, be left with x squared plus 2y equals negative 2xy. And finally, I will divide through. So dy dx, and I divide through by this piece here, so it divides out on the left and on the right. We get negative 2xy over x squared plus 2y. Okay. All right, now let's go try to plug everything in. So we start here, and when we plug that in, we get 2x and then y. Oops, 2xy. I'm just going to leave it as y. Plus, now we have x squared plus 2y times dy dx, which is this right here. So times negative 2xy over x squared plus 2y. Question is, does that equal 0? And check this out. The x squared plus 2y, x squared plus 2y cancel here, which means we have 2xy and then plus, and then all that was left there was minus 2xy. Those cancel out, and we indeed get 0. Okay, so that worked out. All right, let's see here. Number 19. I'm going to try and go to 21, and then I'm going to switch to a different video. So 19, x squared dy plus 2xy dx equals 0. And this time, the function is negative x to the negative 2. That was the one that I accidentally used for the previous problem. So we're going to need to first divide through everything by dx. And when I do that, I'll go ahead and write it out. We're going to have x squared dy dx. So we only need the first derivative here, plus 2xy equals 0. Let's go ahead and get that derivative. So dy dx over here, we did that earlier, was negative 1 over x, oh, sorry, not negative 1, it was just 1 over x cubed, because the two negatives come together. And I forgot the 2, so it's 2 over x cubed, sorry. All right, now, at this point, we just start plugging in. So I've got, what we've got here, x squared, and dy dx, which we just said was 2 over x cubed, and plus 2x times y, and remember y right here, was negative 1 over x squared. And the question is whether or not that's 0. So putting this together, what am I missing here? X squared, oh, I see it. I made a little mistake here. That's cubed. That's cubed. I just didn't write it down right. Cubed. And so when I put those two together, I just get 2 over x. And then plus, actually it's going to become minus, but the 2 stays there. The 2 with the negative 1, so negative 2. And then x here over x squared, just have an x on the bottom. These are exactly the same, just opposite in sign, so those are indeed going to add up to be 0. Okay, taking a look at number 20. Okay, y prime cubed, nonlinear, plus x y prime equals y, and the function we're given as y is x plus 1. So I'm only going to need a first derivative here, but I'm going to have to cube it when I'm done. But that's going to turn out to be not that big of a deal because the derivative of this function is just 1. So we're ready to roll here. So I'm going to go here, it's going to be 1 and then it's cubed plus x times y prime, which again is 1. Does that equal y? And remember y over here is x plus 1. So does that equal x plus 1? That's the question. And this is 1 plus x, and yes, that equals x plus 1. Yes, that works. All right, last one before I pause here, or stop the video and start another one. I'm going to be doing that because these problem sets take a long time, and I just need little breaks in between. So I suggest you do the same thing. Okay, here's our equation. Got y squared is equal to some constant times x plus 1/4 of the same constant. All right, in this differential equation, I'm going to need the derivative. Yes, I will need to square it also, according to this, but let's just take the derivative. All right, so we're going to need some implicit differentiation. All right, derivative here on the left side is 2y times, now derivative of the base here, which is, I'm going to use the prime notation there. So the derivative left side with respect to x is 2y prime. Now derivative of the right, the constant out front is going to just stay there. Now just do derivative of what's in here, and these are separated by addition, so I'm doing them individually. Derivative of x is 1, and the derivative of 1/4 of a constant is just going to be 0. So we have 2y, y prime is equal to that constant c sub 1. And so if I want to solve for y prime, I just divide through, so it'll be c sub 1 over 2y. All right, let's go and plug and chug and see what happens. So as I start moving here, y is y equals 2x times y prime. So here comes y prime at c sub 1 over 2y. And then plus y times y prime, which is c sub 1 over 2y, but all of that cubed. And the question is, are these equal? All right, so this looks a little messy. Y equals, all right, when I put this together here, the 2's cancel, so I just get the x times the c1 on top, and then over y. Now, on the right, or on the second term on the right, the y's cancel. Oh, no, they don't. Oops, I forgot the cubed. So I cubed first, so I'm going to have y times, it's going to be c sub 1 cubed over, when I cube the bottom here, I get 8y cubed. All right, this is looking pretty bad. So y is equal to x times c1 over y. And we're wondering, is this equal, right? Are these the same? And then plus, one of these y's cancels, so I get c sub 1 cubed over 8y squared. All right. Oh, boy. So what can I do here to see if these are the same? On the right-hand side, let me get a common denominator. So I'm going to try and get a common denominator between these two right here. So I'm going to have to introduce an 8y here and an 8y here. Let's just see what happens. So my question is this the same as? Okay, when I put all that together, it's going to be, I'm going to write it as 8xy c sub 1 over my common denominator, but I'm going to be putting that together with c sub 1 cubed. Okay, so that's going to be putting that together with that, all over the same denominator, 8y squared. Now, we know what y squared is. That was given to us up here. Okay, that's kind of the reason I got that common denominator. Let's remember up here that y squared was this, right? Okay, so let's just plug that in and see what happens. If I take, I'm trying to squeeze all this in here. Okay. If I take this, the question is, does y equal 8xy c sub 1 plus c sub 1 cubed over 8 times that thing up there in yellow, so c sub 1, and then x plus 1/4 c sub 1. All right, let's see what happens to this thing, if we can get something nice to happen here. In the numerator, let's factor out a c sub 1. So I'm going to move over here so I have some more room. Does this equal, factoring out a c sub 1 from the top, yeah, just a c sub 1, we get 8xy plus c sub 1 squared. And on the bottom, what I'm going to do is I'm going to go ahead and multiply this 8c sub 1 through, but I think I'm going to leave, I'm just going to multiply the 8 through and leave the c sub 1 out there because it's going to cancel with the 1 up top. So just the 8 through there, I get 8x, and then I get plus, when I multiply 8 times 1/4, I get 2c sub 1, and that's it. C sub 1's cancel. Now, gee whiz, this is nasty. So does y equal 8xy plus c sub 1 squared over 8x plus 2c sub 1? Alright, we can't play with both sides, but give me just a second. Let me check something here. I want to make sure I didn't make any mistakes, but I don't want to waste your time. Okay, I see what I did, and I feel like an idiot. There's not much I can do to recover from this. Up here I had that squared, and when I put it in here, for some reason I put cubed. And you were probably sitting there going, why did you do cubed? That's squared. That changes a lot of things here. So when we square this, it's going to be squared here, it's going to be squared here, and this is going to be a 4y. Now, how does that change things? Let's see. Let me go back to this line. Hey, baby. You okay? Okay, yeah, that's fine. Sorry, my daughter came in here. She's came into my office to get something. Okay, so back to this. Oh man. See, it's just part of being in this subject. It's just little mistakes. You know, everybody makes them. Okay, so let's see here. This y cancels, and then one of those y's cancels. So I just get c sub 1 squared over 4y now. And let's see here. What happens at this point? Make sure I didn't mess anything else up there. I think I'm good. Alright, so let's just see where we are. Let's get a common denominator. So we get 4 here, 4 here. So we get 4x c sub 1 plus c sub 1 squared over 4y. And the question is that equal to y? Okay, so we're going to have to go back up here and yeah, okay, I see it. I see it. I see it. One more thing to do here was pull out that c sub 1, and we're left with 4x plus c sub 1 over 4y. So pull out that common factor of c sub 1, and then notice that this is, where is it? Oh, I need to pull out a 4. Yeah. Pull out the 4 also. Let me see here. Do it this way. Pull a 4 out, factor 4 out here, and this goes away, and this becomes 1/4. There we go. Now it'll work. So c sub 1 times the quantity x plus 1/4 c sub 1 is this right here. And that is y squared. So what we get here is 4y squared over 4y. The 4's cancel, one factor goes away, and you just get y. Okay, sorry about that. My only excuse for that is that it is still summer for me. And I'm doing this on my own time here, and so I'm not completely focused yet. So hopefully things will get a little more sharper, I guess, if that's not proper English, but okay, I think that's it. I'm going to stop this video. All right, working now on number 22. All right, so number 22. Boy, this looks weird. Okay, 22. Y prime equals 2 times the square root of the absolute value of y. And then our function here is y equals x, absolute value of x. All right, so we do have a little bit of an issue we need to recall here. Well, I should say that there's what we need, the first derivative. So you might need to remember from Cal 1 that when you take the absolute value of x and you take its derivative, the derivative of that is actually x over the absolute value of x. So here's the idea, in case you didn't cover this in Cal 1. You've got the absolute value of x function looks like a v. So it's like if you are over here to the right of 0, then the slope of the tangent line or the derivative should be 1. So you could get that by just picking some value of x and plug it in here. And if you take that value of x, whatever it is, and divide it by, you know that that would be a positive number because you're to the right of 0. And then if you take the absolute value of that number, it will be the same. These would be exactly the same, so the ratio would just be 1. However, if you were on this side of 0, then what's going to happen is you want the slope of the tangent line to be negative 1. And that's because your slope is negative 1 here. So what you do is, let's say you take a value of x here and you plug it in, and you plug it into this derivative. You have x over the absolute value of x. Just keep in mind that that's going to be a negative number. And then when you take the absolute value on the bottom, it's going to be the same number but positive. And the ratio of those two will be negative 1. And therefore it works out. Now the only thing is that this formula doesn't work if x is 0. But that's okay because the derivative at 0 is undefined. Okay. With all that said, let's continue. So we want to take the first derivative here. And we have a product rule right there. So we do derivative of x, which is 1 times the absolute value of x, plus derivative of absolute value of x, which is x over root x. You can, not root x, x over the absolute value of x. You can also write this the other way, by the way. This can be flipped over. It's the same thing. And then times x. So that's your product rule. So cleaning that up, let's do absolute value of x plus, I'm trying to decide if I want, you know what? Let's go ahead. I should have said that in the beginning, that this right here could be rewritten the other way around. These would give you the exact same results would happen here. So you can use either one. So it's going to just work out nicer if I put it this way, because these x's will cancel, and then all you get is root x plus root x, which is 2 root x. All right, so that's our derivative. Now coming back and plugging in, so the derivative is 2 root x, and we want to know, is that equal to 2 times the square root of the absolute value of y. So what we want is, let me check out what this is here. The absolute value of y is equal to the absolute value of x times the absolute value of x. Okay, which we could, all I'm doing is plugging this in right here for y. So what we can do here is we can say that the absolute value of y is equal to, and then using properties of absolute values, we can do absolute value of x, like basically taking this product and just doing the absolute value of each one. This would be a double absolute value, but that's still the absolute value. So we have the absolute value of x times the absolute value of x, which is just going to be x squared. And that goes here. And then when you take the square root of the x squared, we have to be clear that that is the absolute value of x. That is it by definition. So this becomes 2 root x, and that checks off. That matches the left side. All right. Number 20, let me give you a second to look at that. Number 23 is up next. Real quick, I got to do something, mute this. Okay, 23. All right, we have y prime minus 1 over x y equals 1. And now we're starting to get some interesting functions. Y equals x natural log of x, and we're saying that x is greater than 0, which is what we need to define natural log anyway. So, all right, we only need the first derivative here, so let's take our derivative. Product rule going right down here. That's our product rule. So derivative of that is 1 times natural log x plus derivative of natural log of x, which is 1 over x, times the first function there, which is x. So end of the day here, this is natural log of x plus 1. That's y prime. So we plug that in, and we get natural log of x plus 1 minus 1 over x times y, but remember y was x natural log x. And the question is, does that equal 1? And see these x's cancel. So what you get is natural log x plus 1, and then minus natural log x. Natural log x's cancel, and you're left with 1, and yes, that does equal 1. So we're good to go. 24. The derivative of capital P with respect to t equals capital P, and in parentheses a minus b capital P, and they tell us that P is equal to a c sub 1 e to the at all of that over 1 plus b c sub 1 e to the at. All right, let's start with a few things here. Our independent variable is t. So that appears here, that appears here. Okay, our dependent variable is p, and so that's a dependent variable right there. So everything else here are constants, all right? So a is a constant, b is a constant, and c sub 1. Those are all constants. So when we take derivatives, let's just keep that in mind. Now I do need the first derivative here. So when I take my first derivative, I'm going to get dp dt equals, now over here I've got a quotient rule. Alright, so what is the derivative of this top function? Because we're doing quotient rule, which is the derivative of the top times the bottom minus the derivative of the bottom times the top, all over the bottom squared. It's going to be messy. So derivative of the top, a c sub 1 comes for the ride. The derivative of e to the at is itself, but then an a is going to pop out, because when we take derivative of at, we're just going to get a. So when that a pops out, that becomes a squared. C sub 1 e to the at. And then we have to multiply that times the bottom. 1 plus b c sub 1 e to the at. And then subtract from that, and I think I'm going to run out of room. Where's my lasso? Let me just move this a little bit over here. Okay. Minus the derivative of the bottom. So I've got two terms here with the plus between them. Derivative of 1 is 0. So the derivative of the rest of it is, I'm going to have b c sub 1 comes for the ride. Derivative of e to the at is itself, but then the a pops out. So I'm going to put that a in front of the b. ab c sub 1 e to the at. That's derivative of the bottom. Now I multiply that times the top. A c sub 1 e to the at. That's finishing off the top part of the quotient rule. And then all over the bottom squared. 1 plus b c sub 1 e to the at. All of that quantity squared. What a disaster looking derivative. But I'm really hoping that things are going to clean up here. I really do hope. And I think I see some things that might happen here. I'm wondering if I should distribute this through first or not. Yeah, I don't think there's any way around it. Let me try and clean it up. Okay, when I take this whole factor and distribute there, times 1 is itself. A squared c sub 1 e to the at. And when I multiply it here to here, let's see, I'm going to have plus. I've got a squared. I've got a b in there. I've got two factors of c sub 1, so c sub 1 squared. Then I got e to the at times itself, which is going to double the exponent. So e to the 2at. Remember, we add exponents when we multiply, so this gets added to this. At plus at is 2at. And that takes care of the distribution. And then these two, it's not distribution, but I do need to multiply these, so I can put the a's together, so that would be a squared. And then I have b. Then I have c sub 1 squared. And I have c sub 1 squared, and then I have e to the a 2t again, 2at. Oh my goodness, are those the same? All over 1 plus b c sub 1 e to the at, but all that quantity squared. So what I'm seeing here is that this looks like this. They're the same thing, but they're opposite in signs. Those suckers are gone. I hope you're getting a sense that I have not worked through these problems because I really wanted to go through them first time on camera or being recorded so that you could kind of see that, you know, things don't always run as smoothly as you would hope, and you just got to kind of grind away at these things. Alright, so there's my dp dt. It's a little nicer. I mean, it's still ugly, but it's a little nicer than what it was. Okay, now I need to check it. So I need to see if that works in this formula. My goodness. All right. I think what I'm going to do here is I'm just going to point out that this right side up here is AP minus BP squared. I don't know if that's going to help, but I'm just going to point out that's what the right side is, and the left side is dp dt. So let me try this now. I'm going to try and see if it works. So I'm going to need some more room. I think what I'd like to do, just to make life a little easier for us, I'm going to take all this out. And then I'm going to bring this up a little bit. Oh, why not? I can't bring this up? Oh, it's because of this over here. Okay, let me try this now. Bring that up here. Okay, that'll give me some room to work down here. So this right here, we just got that to be this piece right here. I'm going to put it right there. Okay, so that is the left side. The question is whether or not that's equal to the right side, which is a times p. So that's, here's p over here. A times that would give me a squared c sub 1 e to the at over 1 plus b c sub 1 e to the at. All right, so that's just a times this. So all I did was added a factor of a to this and made it a squared. Everything else is the same. And then minus, if I do b times this thing squared. So let's talk about what it would mean to square this before. Maybe I should do that up here. What is p squared? Well, it would be a squared, c sub 1 squared, then e to the 2at, because all I'd be doing is squaring each of those factors. Then on the bottom, it would be, well, I just square the whole thing, so I'm going to write 1 plus b c sub 1 e to the at, and I'm just going to put in parentheses and square it. And I'm happy to see that because that does appear here on my left-hand side, so I'm happy to see it. So let's plug, that's what p squared is, and then remember I have to put a b in there also. So I'm going to get here a squared, here's the b, and then c sub 1 squared, and then e to the 2at, then all over the 1 plus b c sub 1 e to the at, and then that quantity squared. Okay, are these the same? Well, doesn't look like it, but I believe we can do something here. We can get a common denominator between these two. So what I'm going to have to do is notice that this right here matches with the one in parentheses here, but this one is squared and this one is not. So to square it means I need to take that and multiply it by itself on the top and the bottom. Yuck, but this is life. Okay, my left side I'm just going to leave it alone. I'm not even going to mess with it right now. But I want to know whether or not that left side is equal to 1 plus b c sub 1 e to the at times what was up here, a squared c sub 1 e to the at, and then minus, that's this, and then a squared b c sub 1 squared e to the 2at all over the common denominator, which was now 1 plus b c sub 1 e to the at, that quantity squared. Okay, what's going to happen now? When I multiply this times this, and then I have to do this times this, I believe, and I want to try and not have to write all this, I believe that when I put this together with this, I'm going to have an a squared, I'm going to have a b, I'm going to have a c1 squared, and when I put the two e to the at's together, I'm going to get e to the 2at. So when I do that green multiplication, it's actually going to cancel with this one because they're opposite in sign. So that's gone. Everything in green is going to be gone. The only thing I really have to worry about now is this distribution right here, here to here. And lo and behold, when you do that, notice that this piece right here, when I multiply that times 1, I get itself, right? And that matches what's here. And then, of course, the denominators were already the same. So check it, check it. I'm not going to do the work. There's just a little bit more to do, but you can see it's going to happen. Awesome. All right, where am I? That was number 24. And we have d capital X over dt. So capital X depends on t. And then we have 2 minus capital X, 1 minus capital X, and I'm using the equation natural log of 2 minus x over 1 minus x equals t. All right, so here we go. I'm going to have to take the derivative. Now x is my dependent variable, t is my independent variable. I'm trying to find dx dt, so I'm going to have to use implicit differentiation. So I'm differentiating this equation, both left and right hand sides, with respect to t. So the right side's easy. Derivative of t with respect to t is 1, but the left side requires some work. So I'm going to make this a little easier. Before I do it, I'm going to use some properties of logs. I'm just going to split this up into 2 logs with subtraction between them. That's just a property of logs. Okay, so I'm just rewriting that first equation. Then when I take the derivative, it's going to be real clean. Derivative natural log of something is 1 over it times the derivative of what's in there, which is -1. Then minus derivative of this natural log is 1 over what's inside, times the derivative of what's inside, which is just -1 again. And so what we get is, oh, I'm forgetting something. What the derivative of what's inside? The derivative of what's inside is not x, it's negative dx dt. We're differentiating with respect to t. So that's your chain rule there. And then same thing here, we're going to get negative dx dt. All right. Let's see if we can't clean it up a little bit. We have negative dx dt over 2 minus x, and then plus, because we have minus and minus, dx dt over 1 minus x equals 1. All right, I'm trying to solve for dx dt, so I'm trying to get this guy by itself. So I'm going to factor it out of the left-hand side, so d capital X over t, and then when I factor that, I get -1 over 2 minus x plus 1 over 1 minus x equals 1. And then I go ahead and divide both sides. Now, d capital X with respect to t equals 1 over. Now when I divide through by all that junk, I get -1 over 2 minus x plus 1 over 1 minus x. Okay, so that's what dx dt is. Looks ugly, but that's what it is. Now, let me go over here, and I'm going to replace this with this. 1 over, yeah, should I get lazy here? I shouldn't call it laziness, I should call it using technology. So there's the left-hand side. Right-hand side is 2 minus x over 1 minus x. And the question is whether or not these are the same. They don't look the same, but we're going to need some algebra here. So what I'll get going now is I'm going to put these two together with a common denominator. So essentially I'm multiplying this up here, and then bringing those two together. So when I do that, I should get -1 plus x, and then plus 2 minus x. Then all over our common denominator, which is now 2 minus x over, times 1 minus x. Okay, that was just what's in blue here. Remember, this is all below this 1. So 1 on top of that means you can flip it. Remember, 1 over x over y is the same as y over x, so I can just flip that. So I'm going to get this fraction flipped over, is essentially what I'm saying, is the left-hand side. So the top is 2 minus x, 1 minus x, looking good. I just need the bottom to be 1. Let's see here, x's cancel, and 2 minus 1, that's 1, so the bottom would have been 1 there. And that does check out, that matches up. Good deal. Where am I at? 26. All right, how am I doing on time here? Go a little bit longer on this one. 26 y prime plus 2xy equals 1. and y, okay, I need to grab this book. Y is equal to e to the negative x squared times the integral from 0 to x of e to the t squared dt plus c sub 1 e to the negative x squared. Okay, craziness here. All right, so let's see if we can't figure out what's going on. This is probably one of the craziest looking problems we've seen. All right, so let's just talk about the derivative, because that's what we need here. We need y prime. So what is the derivative of this? Notice here that this is a product, right? This is a product. And so what we can do is do the product rule there, all right? So let me apply this product rule when we take our derivative. So first thing is, what is the derivative of this? Well, derivative of that's just negative 2x e to the negative x squared. So that's just derivative of e to anything as itself, then derivative of what's up there is negative 2x, and that comes out front. Then you still have the second function, which is still an integral. Okay, and remember, we're differentiating with respect to t here, or I'm sorry, with respect to x, all right? We're differentiating with respect to x. All right, so now what we do is we say plus, because this is a product rule, the derivative of this. All right, so this is very important. This is coming back to the fundamental theorem of calculus. So what this is basically saying is that, I mean, if we could integrate this, we would do it, but we can't integrate that. That's not integrable unless we use power series. So let's just imagine it this way. Let's say that that does have an antiderivative, and let's call it capital F of t, right? Let's just say that's what it is. Then what we would want to do is we would want to evaluate that at this right here. Make sure you understand, I'm saying if that had an antiderivative, it would be capital F of t. Then we would want to evaluate it at x and 0. So what we would get here is we would have capital F of x minus capital F of 0. Okay, so imagine really that everything in this right here is really just this. Now, what would the derivative of that be? Because that's what we're asked to do. We're asked to find the derivative. So if I ask you to take derivative of this, you do each of these individually. So capital F of x, remember, capital F was the antiderivative of this guy right here. So if I ask you to differentiate this, take the derivative of it, you should just get this function right here, but with x plugged into it. So wouldn't that give you just e to the x squared? Yes, it would. And then you'd have to say times, you would need to go minus derivative of this. Now this, on the other hand, this is a constant. And the reason why is because you have a function, you're plugging 0 into it, it's going to spit out a number. So derivative of a constant is 0, so you would have plus 0 here. And that would be the derivative of this. And remember, I'm still trying to do the product rule here. Right? We had done derivative of this times this, that was that, and then plus, now we took the derivative of that nasty thing right there, which was this, and then we still have to multiply times e to the negative x squared. Okay, messy enough for you? And then we still need this plus sign here. We need to take derivative of, hang tight. All right, sorry about that. I had to take that call. Okay, so now what I was doing was working on that little plus sign right here and trying to find the derivative of this piece right here. Okay, so let's not forget that constant there. The c sub 1 comes for the ride. We need a negative 2x to come out. So I'm going to change that to a minus 2x c sub 1 e to the negative x squared. All right, I want to rewrite all that. Okay, y prime is equal to negative 2x e to the negative x squared times the integral from 0 to x of e to the t squared dt plus, now check this out, when I multiply these two together, the zero's gone, okay, so we can just ignore that. When I do that, we add the exponents since they're the same base, and when you take when you take x squared and add negative x squared, you get 0, so it's e to the 0, that's just 1. And then we have minus 2x c sub 1 e to the negative x squared. Beautiful. All right, that's what y prime is. Now, the question is, if I take that, put it here, and then add 2xy to it, do I get 1? So let me, again, use my technology /cheat to copy this and paste it. Oh, yeah, that'll work. So there's your y prime, and then now I'm going to add to that 2 and then x times y. So let's pay attention to this. I'm going to go 2 and then x, and I'm going to multiply that times y. And remember, y is this disaster over here. This is y. Ah, no. That's y right here. So imagine hitting every single term with 2x. So what would that be? Okay, so I'm going to hit this thing with 2x, so that's just going to put a 2x e to the negative x squared integral 0 to x e to the t squared dt. Oh, my d is gone there. dt. So that's multiplying that, and then it's like we have two terms here, okay? So your first term here is everything here. That gets hit with 2x. And then we have to hit that blue part with 2x. So now we have plus 2x c sub 1 e to the negative x squared. All right, does this equal 1 is the question. And look at things here. Negative 2 of these, negative 2x e to the negative x squared integrals, and then isn't this positive 2x e to the negative x squared integrals? These kill each other off. They're gone. And this right here and this right here are going to kill each other off also. And all I'm left with is 1, and it works. I hope by this point you're trying to ask yourself the question, you know, that we're verifying these things, which is great. We're verifying that these things give you solutions to these differential equations, but your question is probably, well, how would you ever come up with this, right? And that's what the course is going to be about. But for now, we grind away verifying. And I think I have time for one more. Let me see how much time's on this video first. Yeah, let me try and do one more. Okay, working number 27 here. This is going to be a messy problem. Looking at this differential equation, I'm going to first divide everything by dx on the original differential equation. When I do that, this is going to go away. This is going to be dy over dx, which is y prime, and then 0 over dx is 0. So that's where we are. But we have the ugly task of taking the derivative of this with respect to x, and we have to do that implicitly. So on the left side, we have a little constant here. It's just going to come for the ride. Then we have to do the power rule right here. So 2 comes out. I'm going to put that in front of the c1. X plus y, that quantity is now to the first power. And then I take derivative of what's inside, and that's just going to be 1 plus y prime, differentiating with respect to x. I'm going to get rid of that 1 because it looks like a prime sometimes. That's the derivative of the left side. Derivative of the right side, we've got a product right there. So the derivative of the first function is 1 times the second function, e to the y over x. Then plus, now we need to take derivative of e to the y over x. So derivative of e to anything is itself. But then you have to take derivative of what's up there. And so we're taking derivative of y over x with respect to x. So we take derivative of the top, y prime, times the bottom, minus derivative of the bottom, which is 1 times the top, all over the bottom squared. So this is really just y prime x minus y over x squared, and that goes right here, y prime x minus y over x squared. And then, don't forget the product rule, we need to finish it off. We've taken derivative of this, so now we need to multiply times the first function, which was x. So there's our derivative, and we're trying to solve for y prime, which is pretty messed up. So notice here that this x, I can cancel out a factor here. So really what's going to happen is that x is going to go away, and that's just going to become x instead of x squared. And now, I guess we've reached a critical juncture here. I'm going to try and get my y primes by themselves. So to do that, let's just first look at this. I can split that up. I can make that y prime x over x minus y over x. And that's just really y prime minus y over x. So that's what's really sitting here. Just a little easier to distribute if I have it like this. Okay. Now, let's distribute this through. So we have 2c1 x plus y. You know what? Let's kill two birds with one stone here. I'm going to take this entire quantity and just pass it through this parenthesis. So when I multiply times 1, I just get itself. And when I multiply it times y prime, I get, just write it this way, y prime, and then I get the 2, c sub 1, and then x plus y. I'm not going to distribute anything out, I'm just going to leave it like that. Then equals the right side, which is e to the y over x. And then now when I distribute here, I get plus y prime e to the y over x. And finally, I get, when I distribute the second distribution here, I get minus y over x e to the y over x. All right, so my y prime terms are here and here. Okay, so I'm going to bring those over to one side of the equation. So I will have, and I'm going to go ahead and factor the y prime out now. So that's just me taking the y prime out of this one. Now when I bring that one over, it's going to become negative, but I'm taking the y prime out. So minus e to the y over x. So the y prime is taken out. And then what's left is the e on the right side, e to the y over x. That's this one. This one right here still needs to be there, minus y over x, e to the y over x. And finally, this piece right here needs to come to the right, so minus 2c1 x plus y, like that. Okay. Final step to get y prime is to divide both sides by this piece right here. So we will get a final expression for our derivative. Over 2c1 x plus y minus e to the y over x. All right, now at this point, it would not be fun to plug that in right here. That would be really a mess. So what we're going to do right now is kind of not very natural, but I want you to see after some torment that this will work. Okay, I'm going to go back up to this original expression here. So notice in my original differential equation, I don't have any c1s in here, right? Just x's and y's and y primes. And in my expression down here for my derivative, I've got constants in here. So what I'm going to do is I'm going to take this equation that I have right here, okay, this one, and I'm going to solve it for c1. So just keep note here, and I'm going to put it down here at the bottom, put it in a little box over here, that c1 is equal to x e to the y over x over, y over x, over x plus y quantity squared. So all I did was I just divided x plus y quantity squared on both sides. Now, something kind of magical is about to happen. All right, I'm still continuing. I have not tried to plug anything in up here to verify. Okay, I have not tried to verify this equation yet. Just trying to get a decent expression for y prime. So I have y prime equals, all right, I'm replacing right now this C1 with this expression right here for C1. So I've got e to the y over x minus y over x e to the y over x minus 2, now here it comes, x e to the y over x over x plus y, that quantity squared. So that's me plugging in the C1. Then I still had x plus y there. Now all of that is divided by 2, and then here we go again, C1, which is x e to the y over x over x plus y, that quantity squared. Okay, done with that, but I still had an x plus y there. Then minus e to the y over x. All right, now this cancels, this squared goes away, this cancels, this squared goes away, and notice that every term, every single term, has an e to the y over x in them. So what that means is I could factor an e to the y over x out of the top, I could factor an e to the y over x out of the bottom, and they would cancel out. So I'm really just going to eliminate the e to the y over x from all terms, which leaves me with the 1. That's this one right here, that's a 1 because I factored it out, minus y over x, that's this one gone, and then minus, let's see here, this is going to be just 2 over x plus y, because that came out. So I still had the minus, I still had the 2, and I still had the denominator, so those pieces were right there. Okay, so that's now the top, and then over the bottom, which is going to be 2x over x plus y, and then minus 1. So that was, again, pulling this e to the y over x out, pulling this e to the y over x out. That's what allowed to cancel out here. Okay, double check I got everything right. Now at this point, there's lots of things we can do, but I think what I'm going to do is just get a common denominator. So between all three of these terms up top, the common denominator here would be x times x plus y. So I'm going to basically multiply whatever I'm missing to create those fractions. So remember, this 1 is like 1 over 1. Let's see what happens here. So I'm going to have an x plus y, that's where that 1 was, minus, now for the middle term, I'm only missing the x plus y, so I'm going to have minus y times x plus y. And then on the last term, I'm only missing the x, so I'm going to have minus 2x. Now all of that is over my common denominator. My common denominator was x times x plus y. Okay, that takes care of the top one. Now in the bottom one, my common denominator between these two pieces right here, these two fractions, is x plus y. That's going to become 2x minus the x plus y is what I'm missing in that second fraction, and then all over x plus y. All right, let's clean up. Y prime equals, all right, I'm cleaning up this numerator here. I get x squared plus xy. And then this is a minus sign, so minus xy. Those are going to be gone. Minus y squared. And then I still have the minus 2x out there. Now I want you to notice something here, because we have a fraction over a fraction, that these two would cancel, so those are gone. I also want you to notice that the entire numerator here, that's actually just going to turn out to be x minus y. So distribute the negative sign through there, and you're just going to get x minus y. So what do we have left here? We have this whole thing on top over this x, but then all of that over x minus y over, if you want to say 1, because that cancel. And then what I can do is, flip this fraction, kind of like we did before. I'm going to flip the fraction. The 1's going to come up here. The x minus y is down here. I'm multiplying. And then it's essentially gone down here. And I think we're going to have a final expression for y prime here, because remember, that went away and that went away. So my numerator looks like x squared minus y squared minus 2x, and then all over, when I multiply this times this, I get x squared minus xy. Okay. I feel like I missed a sign here. Let me just double check. Get a common denominator here. Got x times x plus y, negative y times x plus y. And then here, this one was only missing the x. Okay. All right, so now that I've got this here, let's see what happens if I take, I gotta erase a bunch of stuff. Instead, let me grab the original differential equation up here. Grab this, copy it, and let's put it down here. All right, so let's see what happens. All right, if I'm now checking this to see if it works. X squared plus y squared plus x squared minus xy times y prime, and y prime is this. So we have in the numerator x squared minus y squared minus 2x over the denominator, which is x squared minus xy. And these cancel. Something is off. Something is off. Hold on. Let me just double check some things here. This was all good. Quotient rule. Distribution. This is all good. C1, did I solve right there for C1? Distribute x, x, y, got that, x plus y squared. Wrote that, and then minus y over x, this is good. Minus 2c1, so c1 was x, y, x, e to the y over x, and then over this squared, and then these canceled, and then 2c1. Hold on, I'm getting a phone call. Okay, sorry about that. Got a phone call. But while I was on the phone, I found the mistake. Right here, when we were up in this step, everything's good, but remember when I was saying factor out the e to the y over x, e to the y over x, and I said, what would we have left here? It was supposed to be minus 2x over x plus y, and I didn't put that right here. I just put 2. So let me put that x in here, and let's just see what happens. I've got x here. Then what we did is we got a common denominator, so I had to multiply this by x times x plus y on the top, this by x plus y on the top, and this by just x, and that would have turned this into an x squared. You see that right there? Then, when we did our distribution through here and through here, the only difference is this last term would be x squared, and then this would be x squared here, and then when we did our y prime, this would be x squared here. These would cancel, but now we actually have some good stuff. We've got x squared plus y squared and then we have plus, and then x squared minus y squared minus 2x squared. And the y squareds cancel, and all the x squareds cancel, and we get 0. Okay, sorry about that, but I hope that makes sense. All right, let's move on. Number 28, I believe. Yeah. All right, I can't read this, too dark in this room. Okay, y double prime, second derivative finally, plus y prime minus 12y equals 0. And the function we're working with is y equals c sub 1 e to the 3x, golly this thing, and then plus c sub 2 e to the negative 4x. We're going to need two derivatives here, first and second. So let's get them. Y prime equals 3 c sub 1 e to the 3x, chain rule, minus 4 c sub 2 e to the negative 4x, chain rule. All right? So I'm assuming you're comfortable with those derivatives of e's now, especially when there's linear expressions up in the exponent. Our second derivative, we're just going to go again. So we're going to have another 3 pop out here. We're going to have 9 c sub 1 e to the 3x. We're going to have another negative 4 pop out. So plus 16 c sub 2 e to the negative 4x. So now let's just plug everything in. All right, so y double prime is 9 c sub 1 e to the 3x plus 16 c sub 2 e to the negative 4x. Then we're going to go plus y prime, which is 3 c sub 1 e to the 3x minus 4 c sub 2 e to the negative 4x, and then minus 12 times y, and y was given to us as c sub 1 e to the 3x plus c sub 2 e to the negative 4x. And the question is, does that equal 0? So we'll have to distribute these through. And notice that when we combine like terms, we've got 9 of these, another 3, that's 12 of them. But then we're going to distribute this negative through here, and we're going to cancel. It's going to become negative 12 of those. So that, with the negative 12, is going to kill off that. And then when we do 16 of these and we take away 4, we have 12 of those. And then when we distribute through here with that negative 12, we're going to get negative 12 of those, and they're going to cancel out. So we'll get 0. All right, 29. 27 was a monster. All right, 29, y double prime minus 6y prime plus 13y equals 0. And we have the equation here, y equals e to the 3x cosine of 2x. I think I can tell what happened with those problems that I was doing before. When we got to number 27, that was like the last problem where the highest, well, the order was 1, because the highest derivative in there was first derivative. But that was the last problem with the first derivative, so it was by far the hardest. Okay, so now we're starting to get into second order differential equations. All right, so we're going to have to take derivative twice again. So our first derivative, we're going to have a product rule here. There's our product. So the derivative of e to the 3x is 3e to the 3x, then times the second function, and then plus the derivative of the second function. And that's actually in turn to a minus, because derivative cosine is negative sine. And we're going to have a 2 sine 2x. That 2, remember, comes when you take derivative of the argument inside here. And then we have to multiply that times the first function, e to the 3x. All right, and now we need a second derivative. So when we do that, we're going to have two product rules. So I better give myself some room. So I'm working on the fact that I've got a product here and a product there. So let's do my first product rule. I'm going to have 9 e to the 3x, that's a derivative of 3 e to the 3x, and times the second function, plus, but again it's going to become minus 2 sine 2x, but then times the first function, 3 e to the 3x. And that's it for the first product rule. Now the second product rule, I'm going to have minus, and I'm going to do it in brackets here. So I'm really just focusing on this product right here. The negative sign will distribute through when I'm done. So what is the derivative of 2 sine of 2x? That's going to be 4 cosine 2x, then times the second function, so I'm doing product rule, plus the derivative of the second function, which is going to be 3 e to the 3x, and then times the first function, which is 2 sine 2x. That's all in brackets. And let me try and clean it up. See if I've got some like terms here. I've got 9 e to the 3x cosine 2x, and then 4 e to the x cosine 2x, and I'm subtracting 4, so that's going to mean I'm going to have 5 of those. 5 e to the 3x cosine 2x. Okay, so I took care of that and that. And then I've got negative 2 sine 2x times 3, so that's really negative 6 sine 2x times e to the 3x. That's what that is. And then over here I have 2 and 3, that's 6 e to the 3x sine 2x. So another 6 of these, and I'm subtracting, so it should become minus 12 e to the 3x sine 2x. All right, so that's that one. Now let's plug them in. So I've got, trying to check this now. Y double prime is 5 e to the 3x cosine 2x minus 12 e to the 3x sine 2x, and then minus 6y prime. So here's what here's y prime, right? I'm going to multiply it times negative 6. So imagine hitting this with negative 6 and this with negative 6. So that's going to give me minus 18 e to the 3x cosine 2x. And I'm going to hit this right here with negative 6. It's going to be positive 12 e to the 3x sine 2x. So that's this part right here. And then plus 13 times y. So if I do 13 times this, I get plus 13 times e to the 3x cosine 2x. And the question is that 0? All right, where are my like terms here? I've got this has e to the x cosine 2x. This has e to the 3x cosine 2x. And this has e to the 3x cosine 2x. And looks like I have here, between these two, I've got negative 13, then I have positive 13, so those are all gone. And of course, these are exact opposites, so they're gone. So yes, it is equal to 0. 30. Okay, so I'm going to change the notation here. Basically what they're saying is y double prime minus 4y prime plus 4y equals 0. And then they're telling you that y is equal to e to the 2x plus x e to the 2x. Right away, I'm just going to decide to factor that e to the 2x out, like that. Okay, I'm just going to choose to do that. And I need two derivatives of this. So the first derivative is going to be derivative of the first one. I'm doing product rule right there. Derivative of the first one, which is 2e to the 2x times the second one, plus derivative of the second one. So I'm doing derivative of what's in here, and that's just 1 times e to the 2x. Again, I notice that I have an e to the 2x in both. So I have e to the 2x. Factor that out. When I pull that out of here, I'm left with the 2, and I'm left with the 1 plus x. I'm going to distribute that. It's going to be 2 plus 2x. And then when I pull this one out of here, I'm left with the 1, so plus 1. So this is really e to the 2x, and then 3 plus 2x. That's your y double prime. All right, so now let's check it. Y double prime is e to the 2x times 3 plus 2x minus 4 times, let's see, y prime. Y prime was, did I not do, oops, did I not do y prime? Okay, this is y prime right there. Hold on, I'm losing track of what I'm doing here. This was a derivative, and then this, and plus derivative of that times that. Okay, then I pulled out into, oh, I haven't taken the second derivative. Shoot. That was just the first derivative. Okay, my second derivative is going to be 2e to the 2x again times the second function. So I'm using my product right here. And then plus derivative of the second function, this time inside here, which is just 2, and times the e to the 2x. I can do a similar thing I did on the previous one. I can pull out, actually I can pull out a 2e to the 2x this time, because they both have them. Right, they have it here, and it has it here. And I'll just be left with the 3 plus 2x, and then plus the 1 when I pull it out from here. So I've got 2e to the 2x, and then I have 4 plus 2x. All right, there's my second derivative. So 2e to the 2x times 4 plus 2x. And then now I'm doing this part. So minus 4 times the first derivative, which was e to the 2x times 3 plus 2x. And then plus 4 times y. Y was up here, so I'm out of room. E to the 2x. I'll actually write it in this form right here. E to the 2x times 1 plus x. Okay. Okay. So the question is that 0, right? Is this 0? Well, I'm noticing that every one of these things has a 2e to the 2x. All of these have a 2e to the 2x. So let me pull that out so it doesn't get in my way. 2e to the 2x. Now what would I be left with if I did that? I'd be left with the 4 plus 2x from here. I'd be left with, if I pull a 2e to the 2x out of that one, I still have a negative 2. And that negative 2 is going to have to distribute through, so it's going to give me negative 6 and then minus 2x. No, minus 4x, because it's a negative 2 that distributes. And then I'm going to have here, when I pull out of this one, 2e to the 2x, I'm going to be left with a 2, and that 2 has to distribute through. So I'm going to be left with 2 plus 2x. That's what's in here, and I'm hoping that this is 0 in here. So 2x minus 4x is negative 2x, and then add 2x, that's 0. 4 minus 6 is negative 2, plus 2 is 0. So everything in here is 0, and so this out here multiplied doesn't matter. It's 0. Checks. Let's see how much time I've got on this thing. 30 minutes. 31. Yeah, this is a good place to just stop. Okay, you're going to be working number 31 here. y double prime equals y, and that's it. And we have that y is equal to cosine hyperbolic of x plus sine hyperbolic of x. This is going to be pretty straightforward here. Y prime is going to be equal to sine hyperbolic x plus cosine hyperbolic x, and and y double prime is cosine hyperbolic x, my goodness, plus sine hyperbolic x. That should be from Cal 2. You probably need to go back, refresh yourself on the derivatives of the hyperbolic trig functions, but those are the derivatives, no sign changes on those. That's real nice. And so it's pretty obvious to see that these two are equal. So if we plug those in, we get a true equation there. 32. Y double prime plus 25y equals 0. So on this one, we are given that y is equal to c1 cosine of 5x. So we need our second derivative. So let's take our first derivative. That 5 is going to pop out. C1, we're going to get a negative because we take derivative of cosine, we get sine. And then when we take our second derivative, we're going to get a 5 to pop out again. So minus 25c1 cosine. Derivative of sine is cosine, so we don't have a negative that pops out this time. So that's it. So now we just check it here. If we plug in, we get negative 25 c1 cosine of 5x, then plus 25 times this is going to be 25 c1 cosine of 5x. Those are the same quantities, they're just opposite in sign, so yes indeed those will cancel out and you will get 0. Alright, that's smooth sailing here. Sure is better than number 27. 33, y double prime plus y prime squared. So we've got a nonlinear differential equation here, second order. And we're given y is equal to the natural log, the absolute value of x plus c sub 1, and then plus c sub 2. Alright, here we go. So the derivative of this, derivative natural log of something is 1 over it, 1 over the absolute value of x plus c sub 1, times the derivative of the absolute value of something, we already talked about that before, is the absolute value of it over itself, and then times the derivative of what's inside, and derivative of what's inside is just 1, so I don't need anything. And then when you take derivative of c sub 2, it is 0, so you don't need to worry about that. Notice that these cancel, and you just get 1 over x plus c sub 1, which is the same as x plus c sub 1 to the negative 1 power. That's only because I'm going to take derivative again. When I take derivative again, I get negative 1 x plus c sub 1 to the negative 2. Then the derivative of what's inside is just 1, so this is just really negative 1 over x plus c sub 1, quantity squared. Alright, so let's plug this in. If I get y double prime, that's negative 1 over x plus c sub 1 squared plus y prime but squared. So y prime is here. When we square it, we square the top and bottom. So we square the top, we get 1, and we square the bottom, we get x plus c sub 1 squared. And of course, if we add these together, those are exactly the same quantities. So again, we will get 0 when they cancel out. So that was not too bad. Okay, 34. Well, let me scroll back up, make sure you got a good shot of that. Okay, 34 y double prime plus y equals tangent x, and we're given that y is equal to negative cosine x times natural log of secant x plus tangent x. Gonna have to take the derivative twice on this. Got a product rule right there. So our first derivative is, give myself some room here. Alright, so let me go back to that product right there. I've got derivative of negative cosine x is just sine x times natural log secant x plus tangent x. Alright, and then product rule plus derivative natural log of secant x plus tangent x is 1 over secant x plus tangent x, so that's derivative natural log of this stuff. Now derivative of what's inside, derivative of secant x is secant x tangent x plus derivative of tangent x, which is secant squared x. But then I still need to multiply times the first function, which was negative cosine x. So there's my second derivative, extremely ugly, but let's see what happens here. I can probably clean some stuff up here. Notice on this that I can factor a secant out of the top. So when I pull a secant x out of the top, I'm left with tangent x plus secant x, and that cancels with what's on the bottom. So really at the end of the day, this expression right here is just secant x. So I'm going to go ahead and just replace that with secant x. Alright, and secant x is 1 over cosine x. So secant x is 1 over cosine x. And then the cosines cancel, so this is just minus 1 right there. Nice. So this actually cleans up pretty good. Alright, so that's my second derivative. Minus 1. Alright, so let's take, oh, that's only my first derivative. Crap, I need a second derivative. So second derivative, what I'm going to do is, again, I have a product right there. So derivative of sine is cosine times the natural log of secant x plus tangent x, and then plus the derivative of natural log of secant x plus tangent x. We already know, we just did that one a second ago, we know that's secant x, and then times the first function, which is sine x. And that is these two together, that's 1 over cosine times sine, that's just tangent x. And then this is still the same. Okay, so now let's just try this. We take this, which is all of that, okay, and then we add to it this, which is this expression right here. Notice that this and this are exactly the same, except they're opposite in sign, so when I add them, they cancel, and all that's left is that tangent x, and that checks out. So that works. I'll leave that work to you, but I think it's somewhat obvious. 35. X, using some prime notation here, other than the Leibniz notation, what's in the book. Y double prime plus 2 y prime equals 0, and our function is y equals c sub 1 plus c sub 2 x to the negative 1. So we're going to need our second derivative here. So let's get the first derivative. Derivative of c sub 1 is 0. So on the other one, negative comes out. C sub 2 is power rule, x to the negative 2. And y double prime, negative 2 comes out, becomes positive 2, c sub 2, x to the negative 3. So just remember that this is really just negative c sub 2 over x squared, and this one right here is 2c sub 2 over x cubed. So let's go ahead and plug in here. If we take x and we multiply it times 2c sub 2 over x cubed, add that to 2 times y prime, which is negative c sub 2 over x squared, do we get 0? Well, this x cancels in there, we get a 2, so we get 2c sub 2 over x squared, and then that negative pops out, we make this a minus 2c sub 2 over x squared, and yes, check, that adds up to be 0. Alright, this isn't so bad right now. Waiting for the shoe to drop here, number 36. 36 x squared y double prime minus xy prime plus 2y equals 0, and y is equal to x cosine, it's times cosine of natural log of x, and they're saying for x bigger than 0, that's just so that the natural log is defined. And we've got a need for a double prime here, so let me take the first derivative. Got product rule right there. So derivative of the first one is 1 times cosine of natural log x. Then plus the derivative of cosine of something is negative sine of that something. And times the derivative of what's inside, which is 1 over x. And then times the first function, which was x. And those x's will cancel. So we're just going to get cosine of natural log of x minus sine of natural log of x. Second derivative. Okay, second derivative, we're going to take derivative of cosine of natural log of x, which is negative sine of natural log of x, times 1 over x. Inside, take derivative inside, chain rule, minus cosine of natural log of x, times 1 over x. And that should do it. So what happens now when I take this right here? When I multiply x squared times this here, whoa, where'd that x squared go? That's x squared times y double prime, then minus x times y prime. So y prime, I'll just write it down as, whoa, is cosine natural log x minus sine natural log x, and then plus 2 times y, 2 times x cosine natural log of x. Oh my gosh, that's terrible. All right, so let's see here. I distribute the x squared here. And that's that 1 over x is going to hit that x squared. We're going to leave an x on top. So minus x sine natural log x. Same thing with the second term, minus x cosine natural log x. And then when I distribute negative x through here, I get, let me see something. Minus. Yeah, let's see what happens. I get minus x cosine natural log x, then plus x sine natural log x, and then plus 2x cosine of natural log x. And the question is whether or not this is equal to 0. And I see it. Okay, these are gone. And then these two together, that's negative 2 of those. And then I have plus 2 of them here, and that's going to equal 0. So yes, they will cancel. Everything cancels. Beautiful. $37. I have to pause for a second. Okay, where am I? 37. All right, x squared y double prime minus 3x y prime plus 4y equals 0. And we have y equals x squared plus x squared natural log x. And again, we have the condition that x is greater than 0. So we're going to need a second derivative. So my first derivative, I'm tempted to factor out an x squared, but I'm actually not going to do that. So excuse the barking dogs. So that's derivative of x squared plus, now we have product rule right there, so 2x ln x plus derivative of ln x is 1 over x times the first function x squared. So we've got 2x plus 2x ln x plus x. All right. Again, I'm sorry about the dog. If you can hear it. 3x plus 2x ln x. That's y prime. No, y double prime. It's going to be 3 plus another product rule here. 2 ln x plus 1 over x times 2x, which is 3 plus 2 ln x plus 2. All right, so those x's there, we'll cancel that. Oh, and I can put the 3 and 2 together. 5 plus 2 ln x. All right, looks good. Now, plug it in. What is x squared times y double prime? So here's y double prime. Imagine hitting that with an x squared. You get 5x squared plus 2x squared ln x minus, that's my minus now, imagine hitting 3x on this. And how about hitting it with a minus 3x? So it would become minus 9x squared, and then minus 6x squared ln x. And then I have plus, and now I'm going to hit 4 times this. So 4x squared plus 4x squared ln x. And does that equal 0? Let's see. Ooh. Oh, this does not look like it equals 0. Oh, yeah, okay. So 5x squared minus 9x squared plus 4x squared. Those are all gone. And then we have 2 of these, and then we have minus 6 of the same thing, and then plus 4 of those, and so those will cancel. Check. Okay, number 38. Triple prime, y triple prime minus y double prime plus 9y prime minus 9y equals 0. And I've got y is equal to c sub 1 sine of 3x plus c sub 2 cosine 3x, and then plus 4e to the x. All right, I need a triple. I need a third derivative here. Oh goodness. Y prime is 3c sub 1 cosine 3x minus 3c sub 2 sine 3x plus 4e to the x. So that's just some straight up derivative there at the end. I've got a little bit of chain rule with those 3's in here and then switching some signs whenever we take derivative of cosine. Otherwise, pretty straightforward. Now y double prime equals, so we're going to do a derivative of a cosine there, so we're going to get a negative to pop out. And we have to hit that 3 with the 3 again, so minus 9 c sub 1 sine of 3x. Then when we take derivative of that sine, we do not get a sign change, so we do get a 3 to pop out, so minus 9 again, c sub 2 cosine of 3x. And then we take derivative of 4e to the x, we get itself. Third derivative. Okay, taking derivative of sine, we will not have a sign change. A 3 will pop out though, so minus 27 c sub 1 cosine of 3x. And then this time we're taking derivative of cosine, so we do get a negative to pop out. That's going to make that a plus. And 9, that 3 pops out also, 27 c sub 2 sine of 3x. And we still have 4e to the x. All right, checking it all out. If we take this, which is all of that, shall I? Copy that. I'm going to paste it over here. Way over here. Okay, so that's y triple prime. And then minus y double prime. So here's y double prime. Let me erase some stuff so I can copy it. So I'm going to grab that guy. There's y double prime. And I'm supposed to subtract this, so I'm going to change the signs of it once I copy and paste it. Go right there, but I've got to change the signs. So this can become plus, plus, and this will become minus, and that was e to the x there. And then I have 9 of, got to have 9 of these guys in here. So 9 of these. All right, so gosh, I'm going to start running out of room here, definitely. So when I do that, 9 of those, I'm going to just kind of carry it down over here. You get plus 27 c sub 1 cosine 3x, and then minus 27 c sub 2 sine of 3x, and then plus, let's see, 4 times 9, 36 e to the x. So that's multiplying 9 times y prime. Then I need to subtract from this. I'm going to put it down here, minus, I've got to get 9 times y, and y was up here. Y was right up there. This is y. So minus 9 of those. So minus 9 c sub 1 sine of 3x, and then minus 9 c sub 2 cosine of 3x, and then minus 36 e to the x. All right, let's see if we can get things to cancel here. This and this are gone. This and this are gone. This should equal 0. C1 sine 3x, 9 of them. 9 here, minus 9 of them here. Plus 9 of these, minus 9 of these. Minus 27 of those, plus 27 of those, plus 27 of those, minus 27 of those. Everything's gone. 0. We are in business. Number 39. These look like they're starting to get really messy. Y triple prime. Y triple prime minus 3y double prime plus 3y prime minus y equals 0, and y is equal to x squared e to the x. Okay, I've got some product rule to deal with here. I need 3 derivatives, so let's see, 2x e to the x plus e to the x times x squared. I'm going to factor out an x e to the x, and that will leave me with a 2 plus x here. Ooh, do I really want that? That's going to be like a triple. You know what? I'm just going to pull an e to the x out, and I'm going to leave this as 2x plus x squared. And then I'll have a product rule right there. So y double prime, product rule, derivative e to the x is itself, times the second part, plus derivative of the second part, which is 2 plus 2x times e to the x. I'm going to pull out e to the x again and be left with 2x plus x squared plus 2 plus 2x. And that cleans up to be e to the x. And then I think I've got, let me do x squared plus 4x plus 2. And then I got another product there. You can see why I'm factoring out the e to the x. It helps me just a little cleaner with the product rule here. So my product now, derivative of the first one is that, times the second one. And then plus derivative of the second one, which is 2x plus 4 times the first one. And I'll pull an e to the x out again, even though I'm not going to take a derivative. And then I'm combining things, x squared plus 6x plus 6. All right, so that was just me pulling out the e to the x here, and then combining this and this together with addition. All right, let's see what we got. Let's see, y triple prime is e to the x, x squared plus 6x plus 6 minus, let's see, if I take negative 3 and I multiply it times this one right here, y double prime, this one right here, I'll get minus 3e to the x times x squared plus 4x plus 2, and then plus 3 times y prime, and y prime is here. So 3e to the x times 2x plus x squared, and then finally minus y, which is this. So minus, I'm going to write e to the x times x squared, even though it's x squared times e to the x. These things look like division signs. These are not division. Remember, that was just to remind me of product rule in there. Okay. All right, so this should add up to be 0. Let's see. I'm going to have to do a lot of distribution here. So I'll change the order. X squared e to the x. Well, you know what? You know what I could do? I could just pull all the e to the x's out. E to the x, pull it out of everything. So it's really like gone from here, and gone from here, gone from here, and gone from here, sitting on the outside. Then I'm just combining these things. So x squared plus 6x plus 6, and then I have to take that negative 3 and pass it. So minus 3x squared minus 12x minus 6, and I have to pass a 3 through here, so minus 6x, or I don't know why I said minus, plus 6x, and then plus 3x squared. Now all of that in there better be 0. Ooh, that doesn't look like 0. I'm missing something. 3, 12. Oh, I forgot the x squared out here. Oops. Minus x squared out here. Forgot this guy. Okay. So now we should get everything go away. X squared, 3x squared, 3x squared, 6x. Oh, I think I messed up. No, 6x. Oh, I see it. Okay, 6x, and 6x is 12x, and then take away 12x. Okay, so that's 0. Then 6 and minus 6. Okay, yeah, it all works. So that equals 0. Check. Awesome. Okay, number 40. This will be my last one on this video here. 40. Ugh. 40. X cubed, going to use the prime notation, y triple prime, plus 2x squared, y double prime, minus x times y prime plus y equals 12x squared. And here's what y is. Y is c1x plus c sub 2 x ln x plus 4x squared. And they also say that x is greater than 0 here for the natural log to be defined. So I need some derivatives. So y prime is, let's see, derivative of that's just c sub 1. Okay, I've got to do a product rule right in here. So let me just do that right up here. This is going to be natural log x plus 1 over x times x. So that's going to be natural log of x plus 1. But then I need to distribute the c sub 2 through. So how about c sub 2 natural log x plus c sub 2. So that was like, this was in parentheses when I took the derivative product rule there, and I passed that c sub 2 through. And yeah, that's 1, keep in mind. Alright, so that's that, and then, at the end I just get 8x. Okay, first derivative wasn't too bad. Second derivative, I got a bunch of constants in here, so I do get a c sub 2 times 1 over x, and then plus 8, because the derivative of c1 is 0 and derivative of c2 is 0, so the only thing I really have is that natural log and the 8x to worry about. And my triple prime is negative c sub 2 over x squared, and that's it, because I'm treating that as x to the negative 1, just doing power rule derivative on that, keeping the c2 out there. Derivative of 8 is 0. Alright, so what happens if I take x cubed and I multiply it times this? Oh, that didn't work. If I take x cubed and multiply it times this, I'm just going to get an x left on top with that c sub 2, so negative c sub 2x. And then plus, I'll do this one, 2x squared, and then y double prime. Y double prime is right there. And that's going to be, I'm going to put c sub 2 over x plus 8. And then minus x times y prime, and y prime is right here, so c sub 1 plus c sub 2 ln x plus c sub 2 plus 8x, and then plus y, that's where I am now, so plus y, and y is, well, y is right here, y is right there, so plus c sub 1x plus c sub 2 ln x, oh, x ln x. Golly, come on. I don't know why it does that. X ln x plus 4x squared. Alright, when I distribute here and here, I get 2x c sub 2 plus 16x squared. I have a minus c sub 2x out front. When I distribute here, I get minus x c sub 1 minus x c sub 2 ln x. That's that one, and then this one is minus x c sub 2, and then this one here is plus 8x squared, and then plus the rest of that stuff that was down there. Oh my. Okay, so I feel like something is way off here. Oh, I should have been distributing negatives. Okay, so this right here, oops, this is a negative right there, negative 8. Okay. So when I put 16x squareds with minus 8x squared, I get 8x squared, and then when I add 4x squared, I get 12x squared. So those all together or 12x squared. And that's what it needs to be equal to, right? Right there. But let's just make sure everything else cancels out. So this right here, that's x ln x times c sub 2. And this is x ln x times c sub 2, but negative, so those are gone. X c sub 1 minus x c sub 1, then x plus x c sub 1 is gone there. And then minus x c sub 2 and minus x c sub 2, that's minus 2x c sub 2. When you add it to this, that goes away. So that's it. The only thing left is 12x squared. That checks out. All right, good. Okay, going to be working a couple more problems here out of the first section. So how about number 47? So for 47, they give you this differential equation, y double prime minus 5y prime plus 6y equals 0. And then they ask you to consider the equation, or the function y equals e to the mx. And they say for you to find the values of m so that this would be a solution to that differential equation. So to do this, what we're going to do is take some derivatives so that we can, plug in here. We need the first and second derivative. So the first derivative of this, we're assuming m is a constant here, is m e to the mx. And the second derivative is going to be another m pops out, so m squared e to the mx. And now let's plug in. So we've got m squared e to the mx minus 5, and then times y prime, which is m e to the mx, and then plus 6 times y, which is e to the mx, and that must be equal to 0. So in order to be a solution, this equation needs to equal 0. So we can easily factor out an e to the mx, and when we do that, we're left with m squared minus 5m plus 6 equals 0. And the only way that this equation would be 0 is if we can get this thing to equal 0, because we know e raised to any power can never be 0. So we've got to really see if we can factor this. This does factor m minus 3, m minus 2 equals 0. So we pretty much can get rid of this because we can divide both sides by that and it's gone. And then now just solving that, we get m is 3 and m is 2. So in order for that to be a solution, we would have to have y equals e to the 3x, or possibly y equals e to the 2x. Those would be solutions to that differential equation. I should say, if we're looking for solutions to this differential equation that come in this form, these are the only two that would suffice. All right, so for number 49, the same situation. We have x squared y double prime minus y equals 0. And we're still looking at the same condition that y would be equal to e to the mx. And we've already taken these derivatives, so we can just plug in. We have x squared, y double prime is m squared, e to the mx, and then minus y, which is e to the mx, and then equals 0. And if we factor out e to the mx, we get x squared, m squared, minus 1 equals 0. And the only way for this to be true, again, we can get rid of this because that can never be 0, is we can factor this as a difference of squares. Xm plus 1 times xm minus 1 must be 0. And that would mean that xm plus 1 would have to be 0, or possibly xm minus 1 would have to be equal to 0. And so let's solve these for m. So if I subtract 1 from both sides and divide by x, And then over here, if you do the same thing, you get 1 over x. So that tells us that in order for this equation e to the mx to be equal, to be a solution, we're going to need m to be either this or this. And if we plug those in, let's plug in that first one, negative 1 over x times x. That's just e to the negative 1. And the other possibility is e to the 1 over x times x, which is just e. So we would be looking at y as being a constant, either e or y equals 1 over e. That's the same as e to the negative 1. Let's see, what number was this, 49? Did I write that down wrong? Hold on. I think I wrote that down wrong. Something's wrong. Minus y. Oh, you know what? I totally jacked this thing up. That was a good exercise, actually. But I messed this up because the instructions for 49 do not have us using e to the mx. They have us using x to the m. Oops. Okay, well, let's redo it. I shouldn't tell you this, but it is 1 o'clock in the morning right now, so that's no excuse. But I should be asleep, but I'm trying to finish this section up tonight, so... Okay, so let's take some derivatives. The first derivative here is m, so this is power rule, x to the m minus 1, and then y double prime is m still out here, the m minus 1 drops down, then x to the m minus 2. And so when I come in here, plug in, I've got x squared times y double prime, which is m, times x, times m minus 1 times x to the m minus 2. And then I have minus y, which is x to the m, and we need that to be equal to 0. So notice there's something we can do here. We have x to the second power and x to the m minus 2. If we multiply those together, we add the exponents. We should just get x to the m, and then minus x to the m equals 0. And now we will factor out an x to the m, and we will be left with m times m minus 1, and then minus 1, because we pulled out that x to the m here. And that's just x to the m, and then we have m squared minus m minus 1 equals 0. And so the question is, you know, for what values of m will this be 0? And this right here can't be 0, all right? That's not going to be 0 unless possibly x is 0. But if x is 0, this is really a trivial problem because you're just going to get that if this is 0, then this whole thing's gone, and then this right here is y, and y would be, if this was 0, it would be 0 to any power should be 0, except for m is 0, but we're going to not even think about that right now. Basically, y would be 0, so that would be true. It's kind of a trivial solution. So we're not considering x to be 0 here, so we're going to chunk this. That can't ever be 0. And now we're just going to say, you know, when is m squared minus m minus 1 equal to 0? For that, I'm going to use a quadratic formula. So I'm going to be using negative b plus or minus square root b squared minus 4ac, all of that over 2a. You've heard that before, done that before. So this is going to be 1. M must be equal to 1 plus or minus the square root of b squared, which is 1, minus 4 times a, which is 1, times c, which is negative 1, all over 2 times 1, so that's 2. So m must be equal to 1 plus or minus the square root of, that looks like we're going to have 5 under there, all over 2. So looks like we're going to have 2 possible solutions here. I'm not, well, I guess we could write this down. If we had x raised to either one of these, 1 plus or minus root 5 over 2, so x raised to that power, if y is equal to that function, it is a solution to that differential equation. All right, moving along, 51. And I forgot what I named this, hold on. I'm going to stop at 51, or am I going to do 52 also? I don't know, let's see. 51, okay, so it says, show that y sub 1 equals x squared, and y sub 2 equals x cubed. Show that those are solutions to x squared y double prime minus 4x y prime plus 6y equals 0. Okay, so let's show that first. So these are 2 different solutions. We have to show each one. So let's start with the first one. Y sub 1 equals x squared. If I take the derivative of that, I get 2x. If I take derivative of that again, I get 2. So if we're treating this as our y function, then we're going to have x squared, and then y double prime is 2, minus 4x, and then y prime is 2x, and then plus 6 times y, so 6x squared equals 0. So this is 2x squared, and then this is minus 8x squared, and then plus 6x squared, and that will be 0. So that checks out. So that is a solution. Now if we look at a different possibility that we use x cubed, then the derivative of this would be 3x squared, and then the second derivative of that would be 6x. And if we go through this same check, and go through it right here, we get, oh, I erased the equation, hold on, come back. Oh yay, I brought it all back. Okay, so there we go. So let's check this. X squared times y double prime is 6x, minus 4x times y prime, which is 3x squared, and then plus 6 times y, which is x cubed. Does that equal 0? Well, this is 6x cubed. This would be minus 12x cubed, and then plus 6x cubed. Yeah, that's all going to cancel out, so that works. So we've shown that these are both solutions. All right, that's the first part. So both of these work. Now, it says, are the constant multiples of C1, C1y1 and C2y2 with arbitrary constants also solutions? So what they're saying is, if we do, let's just call this, let's look at y equals C1 y1, which is really just C1 times x squared. The question is that a solution? Okay, so let's take derivative. Y prime would be 2c1x, and y double prime would be 2c1. So checking in here, we'd have x squared, y double prime is 2c sub 1, minus 4x times y prime, which is 2c sub 1x, plus 6y, and 6y would be c1x squared. Is that 0? Well, let's see what we've got here. Let me just double check I'm doing what they say. Okay, are these solutions? So x squared times 2c. So this right here is 2x squared, c sub 1, minus, next one's 4x squared, I'm sorry, 8x squared, c sub 1, and then plus 6x squared, c sub 1. So yes, this is 0. Check. So that works. And then they want you to check whether or not another one, I'm out of room on this page, but I'll squeeze it in here, is y equals c2 y sub 2, which is c2x cubed. Is that a solution? So the first derivative of that is 3c sub 2x squared, and the second derivative is 6c2x. So when we start plugging in now, we get x squared times 6c sub 2x, and then minus 4x times y prime, which is 3c sub 2x squared, and plus 6 times y, which is c sub 2x cubed. Is that 0? That's the question. So this is 6x cubed c sub 2 minus 12x cubed c sub 2 plus 6x cubed c sub 2 equals 0. Yes, that is true. We got all this cancels out. So those are both solutions. Now, the final thing is the question of whether or not y1 plus y2 is a solution. So it's asking if I take these two and add them together, is that a solution? So I'm going to just squeeze that in here. So y, if we call y equal to y1 plus y2, this is going to be the same as, just make sure, yeah, x squared plus x cubed. So y prime is 2x plus 3x squared, and y double prime is 2 plus 6x. So let's check it. X squared times y double prime, 2 plus 6x, and minus 4x times y prime, which is 2x plus 3x squared, and plus 6 times y, which was x squared plus x cubed. Does that equal 0? You should recognize that if you distribute on the first distribution, that's the same as the work we did for that one, and that came out to be 0. And then on the second distribution, that's the same work that we did for this one, so those add up to be 0. So you can check it yourself by distributing, but it should work. So therefore the answer is yes. Wondering if we should do 52. I think I'll leave 52 for you. Things are not as nice with 52, but I think that'd be worth you working on your own without me showing it to you. So that is it. We are done with this one. 1-1 or 1.1 in the books.